Hi! At this point, my homebrew computer can run code, read keyboard input, and even play audio samples. Naturally, the next step was to give it a mouse. Not a modern mouse, of course. We're talking vintage serial hardware, 1200 baud, 3-byte packets, and all the quirks of RS-232. What could possibly go wrong? Additionally, I will give you some tips if you have problems with your ACIA module. If you're new here, this is part of an ongoing project where I'm building an 8-bit computer from scratch, one module at a time. The whole thing is based on Ben Eater's excellent 65C02 computer series, but I'm adding a few ideas of my own along the way. So far, we've built a real-time bus debugger using only TTL chips, a working CPU module with RAM and ROM, and an I/O module with a keyboard, LCD display, and even a tiny sampler that plays audio from EEPROM chips. All of it runs on a homemade 40-pin bus I call SEBA1, which stands for Short Extensible Bus Architecture. In this episode, we're turning my homebrew computer into a mouse-controlled machine. Not a USB mouse, of course, we're going full retro with a serial mouse over RS-232. With the help of the hero of today's episode, 65C51. To make it happen, I went online and bought a small pile of 9-pin serial mice. Some old, and some new. Yes. It turns out that in 2025, you can still buy brand new RS-232 mice. So I picked the weirdest one I could find and plugged it in. Now all I had to do was figure out how to make it work. And if you think getting this kind of mouse to work is easy, let's just say it has its own idea of plug and play, and it's mostly no. The mouse I'm using follows one of Microsoft's early serial protocols. It connects to a standard DB9 port and sends data in neat little 3-byte packets, one for each movement update. Communication is unidirectional. The mouse just talks and the computer listens. Just pure 1200 bits per second, 7 data bits, 1 stop bit, no parity. Each update consists of 3 bytes. Bit 6 is always high in the first byte to indicate the start of a new packet, unlike the second and third bytes, where it's always low. First byte includes button states and the 2 most significant bits of the X and Y movement. The second and third bytes contain the lower 6 bits of each axis. Together, these values are combined and interpreted as signed deltas for X and Y. Now let's look at the hardware. Connecting a serial mouse isn't just a matter of plugging wires into TX and RX like we did in Ben Eater's videos. RS-232 has, let's call them legacy design decisions. On paper they make sense, but in practice they are confusing, and I had to learn that the hard way. The first thing I ran into was this: DTE and DCE. DTE means data terminal equipment, usually a computer. DCE is data communications equipment, like a modem, or in our case a mouse pretending to be one. The meaning depends on which side of the connection you're on. In Ben's video, our 6502 is acting as the DCE, and the computer with the terminal is the DTE. But when we connect a mouse to our 6502, the roles swap. The 6502 becomes the DTE, and the mouse is now the DCE. The RS-232 standard says, DTE transmits on pin 3, receives on pin 2. DCE does the opposite, transmits on pin 2, receives on pin 3. Each side's TX is wired to the other's RX. At first, I didn't realize that. I was trying to use the same wiring I used to connect to the computer, but this time with the mouse. After some frustrating attempts, I stumbled upon a diagram online, and suddenly everything made sense. Depending on the device's role in the communication, whether it's the talker or the listener, the wiring has to match. And it's not just about swapping RX and TX. You also need to reroute other lines, like RTS, which was used in Ben's video and is crucial here, along with DTR to power the mouse. There's no power pin in RS-232, so the mouse pulls a few milliamps from signal lines like DTR and RTS. Since my ICL-232 only had one spare output available, I added a jumper on the board to route the same voltage to both RTS and DTR, so that the mouse gets powered regardless of which line it's expecting. As you can see, it works. Getting it all right takes a bit of effort, but once you do, everything clicks into place. Time to see it in action. First, I started with the basics, just printing a 1 or 0 to the LCD, depending on which mouse button was pressed. The program handled serial interrupts and tested the bits inside the packet. But in the final version, the LCD shows much more. Button states, direction, and cursor coordinates in a 0 to 255 range. All that decoded in real time from 3-byte packets over RS-232. If you're curious about the code, there's a link in the video description. Now, let's move on to what else I've learned about the 65C51. If you built this module based on Ben Eater's videos, you might be interested in a few small details I ran into. Nothing major, just things that might save you a bit of confusion. A lot of these quirks I figured out thanks to a really helpful thread on Reddit, so thanks Reddit. First of all, if you're using the Rockwell R65C51 like I did, there's some good news. Unlike the WDC version Ben used, this one doesn't suffer from the bug where the transmitter data register empty flag is always set in the status register. Oh, so it's not a bug anymore. Let's talk about MAX232. Lot of builds, including Ben Eater's just work, but some people, including me, often use drop-in replacements like ICL232. They are technically compatible, but in practice not always. Here's my advice, which I learned the hard way. Always check the datasheet for your exact part. For example, the Texas Instruments datasheet for MAX232 says that capacitor C3, the one connected to pin 2, can go to either VCC or ground, and in Ben's video, it's wired to ground, and works fine. But my chip was an ICL232, and it turns out it really didn't like that. With C3 going to ground, the chip would hang and pull way too much current. The documentation for the ICL232 shows to connect C3 to the power line. Connecting C3 to VCC worked, stable communication and no problems since. And the last tip, especially useful if you're just wiring up your ACIA for the first time. Tie the DCD and DSR pins, that's pins 16 and 17, directly to ground. If you don't, the chip might randomly trigger interrupts, and those interrupts will trigger your headache. And while you're at it, ground CTS as well. Leaving it floating can cause more mystery bugs than it's worth. Pay attention to those little details and the whole thing should hopefully just work. I've included a schematic diagram in the video description in case you want to have all the connections. Now, let's take a look at the board layout. At the heart of it is the 65C51 chip, responsible for sending and receiving data over RS-232. Right next to it is a crystal oscillator that sets the timing needed for reliable UART communication. Next to it is a MAX232, or in my case, an ICL232 CPE, that handles voltage level conversion between the chip's TTL logic and voltages used by RS-232. There are two connectors, a female port, like in Ben Eater's videos, used to connect to a computer, and a male port that I added specifically to plug in a mouse. Just like in the previous episode, I'm using a 74LS684 address decoder to assign a memory page in the available memory space. This time though, I've replaced the usual jumpers with a dip switch, way easier to adjust. Here's also a power input, and the standard SEBA 1 connector. Although in this episode, I've actually added power lines directly to the SEBA 1 bus to make voltage distribution more stable. So that was my ACIA module. If you found this video useful, give it a thumbs up and consider subscribing. And I'd love to invite you to the final episode of the series, the grand finale, where all the modules come together into a basic but fully functional computer. We'll render a full 40 by 25 text screen, controlled directly by the 65C02 and the legendary CRTC 6845 with help from a dual-port static RAM. That video module was actually the reason I started this entire project. So, see you next time and thanks for watching.